Hi, in this video we'll talk about perceptual learning and spatial memory. Perceptual learning produces more effective or efficient processing through repeated exposure to a class or category of stimuli. Those with extensive experience may be able to identify subtle differences that distinguish highly similar stimuli. To the untrained eye, male and female chicks may look identical, but chicken sexers can tell the difference in a matter of seconds. I may be unable to tell the difference between an authentic designer bag and a fake reproduction, but fashion designers and maybe some of you could with little difficulty. If you feel insecure about your perceptual skills, don't worry. Perceptual learning can happen even if the learner is not aware that her sensitivities to perceptual differences are increasing. Although many of us may not have extensive experience identifying the sex of chicks or authenticity of designer clothing, almost all of us has acquired advanced expertise in identifying faces. This may not seem like an amazing accomplishment, but think about how similar faces are. As a class of stimuli, it's very homogeneous. Almost all faces consist of the same basic components, and subtle differences in configuration distinguish one face from another. Yet you have no problem identifying your friend in a crowd. With all the technological advances, AI can't begin to rival us in this domain. This has led cognitive researchers to question whether there might be something special about facial recognition compared to other types of visual identification tasks. And our processing of faces seems to be somewhat unique. For instance, we see an orientation effect for faces. It's more difficult for people to recognize inverted or upside down faces compared to faces that are right side up, or compared to other inverted objects. Inverting houses doesn't seem to disrupt identification, but researchers found that inverting photographs of faces did. Researchers have also documented the Thatcher Effect. We have difficulty sensing the unusual orientation of features in an inverted face, but can readily sense this in a face that is right side up. These effects have led to the theory that facial perception rests heavily on configuration. It's not the individual features that matter, but the relationships between the features. How far apart are the eyes? How close is the mouth to the nose? The fusiform face area is thought to specialize in facial perception and other types of visual processing requiring perceptual expertise. Increased activation is observed in this area when we view photos of faces, but not other types of visual stimuli. However, when car experts are shown photos of cars or bird experts look at birds, there is increased activity in this area. But as a non-bird expert, I wouldn't have increased activity in the fusiform face area when viewing photos of birds. This suggests that this area plays a role in visual expertise, and that activity in this area is dependent upon experience. We have a lot of experience identifying faces, and we develop expertise in this domain. However, many people may only have extensive exposure to faces within their own race. So while they may be experts in identifying faces within their own race, they may lack expertise in identifying faces of another race. Keep in mind that it is thought to be dependent upon experience. What matters is how much experience you have viewing, perceiving, and identifying faces of different races. Those with minimal experience identifying members of a different race may rely less on the global configuration of the face and more on discrete features. This can be problematic because many faces may share similar features, leading to identification errors. Check out the video on the other race effect and the video about eyewitness identification errors in your slides. Researchers at Stanford found that the fusiform face area showed greater activation for Owen race compared to other race faces, and that activation in the fusiform face area was positively correlated with identification accuracy. So we can think about the potential to use fMRI to test the reliability of eyewitness testimony, potentially in the future. The perceptual expertise in facial recognition is thought to be the result of mere exposure to a wide variety of faces. We don't intentionally train to be face experts. Mere exposure to physical environments may similarly produce learning of spatial relationships outside of conscious intent. Simply due to experience, you learn how to navigate your environment. This incidental or latent learning has been demonstrated with rats. Tolman randomly assigned rats to two conditions. In the control condition, rats were placed in the maze and were rewarded for completing the maze on every trial. In this condition, we see a steady, gradual learning curve. Over each trial, they were able to solve the maze slightly quicker. In the experimental condition, rats were placed in the maze but weren't rewarded for solving it until trial 11. At trial 11, we see a steep learning curve. They were dramatically quicker in trial 11 compared to trial 10. This can only be explained if the rats were learning the maze in the first 10 trials, despite not being rewarded. The results suggest that rewards may be necessary for the demonstration of learning, but not for learning itself. Merely being exposed to the maze and freely exploring it was enough. They learned in the absence of goal-directed intent. But the question is, what did they learn? The behaviors would argue that to navigate our environment, we learn a fixed sequence of responses. Walk 5 steps, turn right, walk 3 steps, turn left. This doesn't fit well with Tolman's results. If we learn during unstructured exploration, navigation is probably more flexible than a fixed action pattern would allow. Other studies support this theory of flexible navigation. Rats' maze performance isn't disrupted when their starting position changes, but is disrupted if the location of the goal changes. In changing their starting position, we change the sequence of actions. Rats have no problem modifying their action patterns. By changing the location of the goal, we change the spatial relationships in the environment. All of this should make sense. If you've explored DFW, you could find campus whether you started in Dallas or Fort Worth. But if we suddenly secretly moved to the campus, you might have a hard time getting there. So what we learn are the spatial relations between objects centered on our environment rather than fixed behaviors centered on us. It matters where the goal is, not where we are. Landmarks, usually visual cues, are key. If we alter the landmarks, we alter the spatial relationships and disrupt navigation. Researchers moved the landmarks surrounding wasps' nests, and in doing so, disrupted the wasps' ability to find their nests, suggesting that they were relying on those pine cones as landmarks for navigation. If rats are placed in a random location in a radial arm maze like this one, they can learn to use visual cues displayed above the maze to orient themselves and solve the maze. This is also how rats solve the Morris water maze. In this maze, a platform is hidden below opaque water. The rat must learn visual cues to navigate the pool, to swim and find the platform. The hippocampus seems to play an important role in spatial learning. Rats that have damage or lesions to the hippocampus cannot learn the spatial relationships between objects and use this to navigate the Morse water maze. This disturbance was not observed in rats that had damage to another part of their brain. O'Keefe won the Nobel Prize for his discovery of hippocampal place cells. These are neurons in the hippocampus that fire according to physical location. If we measure activity of these place cells as a rat solves a maze, we can basically construct a neural map of the maze. The neural firing pattern is a cognitive representation of the environment. Further evidence of the role of the hippocampus in spatial memory comes from studies of London cab drivers. As cab drivers learn to navigate the complex city streets day in and day out, we see an increase in hippocampal volume. This complex spatial learning produces structural changes in the hippocampus. And so why does all of this matter? One reason is it can help us to understand cognitive impairment in Alzheimer's patients. Alzheimer's is associated with decreased hippocampal volume, and getting lost in a familiar environment is one of the early symptoms. Knowing this, we may be able to use spatial tests to identify the early stages of Alzheimer's development. So in the photograph is me, along with my brother and my grandmother. So my grandmother suffered from cognitive impairment, dementia, likely Alzheimer's, and she would often get lost in a town, a small town, where she had spent basically her entire life. And so that was one of the early kind of clues that she may be suffering from symptoms. And so we may be able to use tests of complex spatial understanding and spatial memory to identify patients who are suffering from Alzheimer's, even in the early stages. So you can test out and see how you do with the 3 mountains test. So you view an image, we remove the image, and then from memory, you have to identify the correct image here from a different perspective. So you have to pick out which is the correct scene viewed from a different angle. And it's actually pretty tricky. So if you're struggling, I did too actually, but the correct answer is marked in green here. All right, thanks guys, bye.